Welcome on our tutorial session Code Inspection with the Javac. My name is Jan Bečička and this is Jan Lahoda. We are NetBeans engineers working for Oracle. Now let's go through this mandatory slide. Today we will talk about parsing. We will talk about Javac, Java model. We will talk about compilation, about invoking Javac compiler. And we will talk about our experience with using Javac as a parser. We have this experience with the NetBeans IDE when we use a Java model for refactoring features and for editor completion and so on. When you are looking for a good Java model, there are several options, or generally two options. You can create your own model, or you can use some existing models and parsers. So why not use Javac? Javac is well tested, not only through Java Compatibility Kit, but also by millions of Java developers. Each language improvement or a language change is immediately propagated into the Javac, and it is used by some products like NetBeans IDE or Checker framework. Today we will do a lot of coding. This is a tutorial session, so we have only a few slides, but we will do a lot of coding today. The source is available at Bitbucket, so you can download the source and code with us. We will use Javac from JDK 7 and for some examples also from JDK 8. And we will use also some pre-created stuff which is available on a Bitbucket. And now I will do a quick introduction to Javac model. It has three main parts. The first part is Javac elements. These are defined in the package javax.lang.model.element. It models classes, methods, variables, type parameters, packages, and formal parameters. It has one-to-one mapping to the source code. It means that each method or each class in a source code has some element in a Javac model. And this part of a Java model goes only to the level of method declarations. It does not go into method bodies. The second part of the model is a type system, which models type mirrors. It is defined in a package javax.lang.model.type, and Java types are, for instance, int type or void type, null type, or j.u.List of strings. One type element, for instance, can have several type mirrors. So type element is, for instance, j.u.List, and it can have several type mirrors like j.u.List of integers or j.u.List of strings, and so on. Utility methods for working with elements and type mirrors are in a package javax.lang.model.util. The third part of a Java C model are trees, which models ASTs, and we will talk about it later in our presentation. Now let's do a first demo.
Thank you, Anne, for introduction. Can you hear me from the speakers, please? Yeah, thank you. So, the first example will be using just the elements and type mirrors, nothing more. And we will basically write an annotation processor because because annotation processors, let me say, implicitly get access to elements and types only. And the example will be on a final annotation and what does it do, or like it's an example annotation, so what do we want it to do? Let us imagine we have an interface like this final interface, and we want just one class to implement this interface. Anyone can call methods on this interface, that's fine for us. Anyone can test for the interface, it's also fine for us. But there should be just one class that will implement the interface. So the advantage of such final interface is that we can safely add methods to it because we control also the implementer of the interface. So in practice, we want to annotate this final interface with an annotation like this, saying that only this final interface impl class can is the allowed implementer of the interface. So this is the valid implementer. And there is another class that tries to implement this interface, and we want to prevent this. Ideally, we want to produce an error and not allow this class to compile at all. So let us create an annotation processor that will do exactly this. And so when one is creating an annotation processor, we typically extend the abstract processor. Then we need to say on which annotations we want to be called, but we want to be called on this class to check whether it's allowed to implement the interface or not, and this class doesn't itself have any annotations. So we will say that this annotation processor should be called on any class, which is basically done through this star pattern. We also need to register this annotation processor into meta services so that Java C knows how to find it. And for that, I will use a special annotation that comes from NetBeans that will automatically generate the entry in meta services for us. I will show you the resulting meta services later, but it allows us simply registering any class for any API type into meta services so that it can be loaded, for example, by service loader. And the annotation processors, if we implement abstract processor, the only method that we really need to fill is the process method, which will be called when compiling some sources. And in this method, we need to, let me say, go through all the classes that are being compiled. And we will do that by going through the root elements like this. First of all, to be on the safe side, we will check that the element we have is a class. And if it's not a class, we will simply skip the processing completely. And now, what we have in the variable e is basically this model for this class. And now we need to inspect all the interfaces it implements to see if the interfaces themselves have the final annotation and verify whether the constraint placed by the final annotation is fulfilled or not. So to get access to the super interfaces of a class, we need to cast to an type element. So I will do just that. And then we will loop through all the super interfaces of the class we have. Yeah. Yeah. Okay. Please, if something is not clear or something is wrong, please tell me, and I will try to fix that or explain it more. Thank you. Now, what we have, if you look at the super interfaces of a class, we see that we don't have any elements. We have TypeMirror, and the reason is that we can have class A that implements list of strings like this. This class, the super interface or the super type of A is not just list, it's list of strings. And to model this exactly, we actually need a TypeMirror. So this is why we get the TypeMirrors as the super interfaces of the class. And now we will need to go from the TypeMirror to an element, and we can do that through a utility class, which is in standard, through a utility method in a standard utility class called types that can, let me say, convert from TypeMirrors to elements if there is an element for the given TypeMirror. So we'll do this here. This is our super interface element. And let me wrap this way. Now we will need to look at the annotations for the super interface element, whether there is the final annotation or not, to check the constraints. For that, we could use this getAnnotation method, which takes the annotation class, but we won't do that because I thought we can do that inside annotation processor, and it works in most cases. When we will go into modeling and into working with the trees, it may be, let me say, wrong to actually load some class for the annotation. So instead of that, I have prepared a utility method that will look up annotation by name. So like the model of the annotation in the Javac model. And this basically all this method does is it iterates through these get annotation mirrors and finds the one that models annotation of the given name and returns the annotation mirror for the annotation. The annotation mirror is basically the model of the usage of the annotation. So let me do it like this. So now, if there is no final annotation on the element, then we can continue to another super interface, and I need to fix this to actually list the super interface. And now, at this point in the code, we positively know that the class we are compiling right now is implementing an interface, and that interface is annotated with the final annotation. And the last thing that we need to check is whether the current class is allowed implementer of the interface. And to do that, we need to check whether the current class is listed here as the allowed implementer or not. And I will use another utility method to get the value of the attribute of the annotation from the annotation mirror. And it will be, in this case, we will get an array of type mirrors modeling the classes that are in the annotation usage. So allowed implementers. And now the last thing we will do, we will go through these allowed implementers and check whether the current class is among them or not. So a very simple loop, and we will again use the S element. Okay. Yeah, sorry, I always forget. Is that fine? Yes. Yeah, thank you. So, and let me close these, and yeah, this should give us more space. We have the class that we are processing here, and we will see if it's any of the allowed implementers. So we will again use this sElement method that converts type mirrors to elements, like this. And if, oops, too few brackets. If it is, then the current class is allowed implementer of this interface, and everything is cool. So we will just continue checking with other super interfaces. But if we are not allowed implementer, which is basically if we get to this point, then we need to produce an error, and we can do that by using the messenger and sending a message to this messenger of type error, and we need to produce some text, and I will cheat a little bit and copy the text from somewhere so that later we have the correct text here. And the text the error basically says you cannot implement the super interface because the current class is, or the class that will get this error is not its allowed implementer. So yeah, this is basically all the code that should do the checking. We just need to return a value from the process method, and we will return false because that means that we didn't consume any annotation, that other annotation processes should still be run on the given class. And now let me build this project And if I will go into the implementer, I will get this error saying, hey, you cannot implement that. And even if I try to build this project, I will again get a compilation error, and the code simply won't compile. But the allowed implementer is fine. It has no trouble implementing the interface. Now, for writing code like this, we could in theory check manually whether we are writing the correct thing or not. But it's very easy to write automated tests for verifiers, annotation processors, and so on like this. So I have written some tests for this tutorial, and the test for this final rule is here. I will run that to see if the implementation is correct. So the implementation is correct. And let me now explain a bit the test framework, so that in the next example we can like use it more easily. Sorry, I
how did you, when you compile it, NetBeans, how did you pick up the rules?
the example project that is the final interface intruder has the project with the annotation processor on its class path or processor path. At which point the javac will find the annotation processors registered in meta services, which I promised to show and didn't so far, and run them. So let me first show how the annotation processor is registered inside. Let's imagine build jar. We have inside directory meta/services. We have a file whose name is the fully qualified name of an API class, in this case, Javax annotation processing processor, which contains the fully qualified names of the actual implementers of that API, in this case, our final rule.
So it goes in meta and services.
Excuse me?
It
Yeah.
goes inside meta and services.
And the javac will look it up from here. Yeah. Okay. Let me go to the test framework. This is a very simple test framework for testing annotation processors and other similar let me say verifiers. We take some class true test, call start a builder on it, and then we specify some input files. So in this case, we are specifying a test input file that implements an API interface, and an API input file that is the actual interface that is not allowed to be implemented at all. Then we say that we want to run some rule, and we say, hey, verify that the warnings provided by this in this case annotation processor match these warnings. So, pardon. This is basically all for this first example, which is mostly on the elements and type mirrors and very simple annotation processors. Are there any questions on this? Okay. So I will have a sip of water and I will continue. So now let me switch to the third piece of the Javac model, the probably most interesting one, and that are the AST trees. And these are let me say, defined in comsound source tree package. This AST like obviously models the whole source tree, including method bodies and everything inside the source code. And the AST nodes have attached elements and type mirrors that somehow correspond to that AST node. We will see an example later. There are quite a few utilities for working with the AST in the util package, and probably the most important one is the trees utility class, which allows us to map an AST or get the element and type mirror from an AST node, and allows us also to go back from an element to the AST node that declares that element in the AST. But to get the trees utility class work in the exact same way as we will use it here, it requires a small non-standard extension, which we'll hopefully show later. So let me show you an example of the AST tree as produced by Javac, and how it's attributed, or how are the elements and type mirrors attached to it. So let us consider we have a variable L, which is of type list of strings, and then we have expression L get 0, which basically means get the very first item from the list. So this is the empty AST. At the very top here, we have the method invocation, the method call itself. Here we have the parameter. It's a simple integer, and here we have this l.get, and it's split into two parts in the AST. One is the, let me say, .get, and one is the variable L, so that if one gets used to this, the model is very neat and very simple. And when Javac attributes this tree and tries to attach the correct types and elements to it, and tries to resolve which exact method we are calling here from list, it starts with the parameters. So it sees that there is just one parameter, which is an integer literal, so it's of type int, and everything is simple. Oh, sorry. And then it goes this way down and looks at this L identifier and tries to look up in the current scope what's the meaning of L, and it finds out that the meaning of L is this variable L. Then it looks, hey, I have this variable L. What is the type of this variable? So it gets that it finds out that it's list of strings, and after that it asks a question. I have a list of strings. I am calling a method get on this list of strings that takes one parameter of type int. Which method I am calling, and it finds out that we are calling the method get with one parameter of type integer, of type int. Actually, this process of resolving the exact method that is being called is not very trivial. It's pretty complex, and especially since Java 5, it's not really something that one could type in 2 minutes. And as the last step, processing this tree, we now know that we are calling a method get on list, and we need to find out what's the return type, so that we can, for example, in the same way attribute some AST node above this current one. And we will find that the return type of this method in this particular case is string. So I would like to ask if there is any question on the AST. Okay, please.
What version of Java is that? Are those packages in?
Uh,
Some source tree. What version of Java is that?
I am pretty sure they are in the tools jar since 6, and I am using 7 in this in these examples. Yeah, it's like it's not standard API at the same level as javax something, but we are using it in NetBeans for a pretty long time to implement basically all features. But it's not at the same level of stability as javax something. Now some maybe asserted facts about the ASTs. The ASTs in Java C are just from the root to leaves. There are links just from top to bottom. There are implicitly no links from leaf to the root. So we cannot go up the AST. And if we need to go at some point up the AST, we need to keep something that is called TreePath, and it keeps all the AST nodes from the root to whatever AST node we have. And we can go up this TreePath, obviously. There are two important utility classes for traversing the AST, going through, let me say, all AST nodes. The TreeScanner, which doesn't keep the current TreePath, and the TreePathScanner, which actually keeps the TreePath that corresponds to the current AST node. Similar visitor scanner pattern can be used also for traversing elements, but it's maybe not used that much often. Sorry. Now, what we will be coding later is we will code some checker, some verifier that will check that some condition is true or false, and these checkers can sometimes be run on code that is not valid Java. And for example, for me, it's inside the NetBeans editor. Most of the features run on whatever code is there right now, which is typically not a valid Java while you are typing the code. And in such cases, the model itself can be a little bit, let me say, surprising, or the data in the model can be sometimes something else that one would expect. So it's good to code defensively. I will try to do that here, but in some cases it may not be defensive enough, even what I will do in this session. In particular, it's good to check for nulls in various places, especially in what we get from Trees.getElement and Trees.getTypeMirror, and we should check what are the kinds of elements and type mirrors. We should not expect that, well, like for example, if you have a class and we look at its superclass, we would expect that a superclass of a class is again a class, right? But it's only true if we are not looking at java.lang object, because there is no superclass of java.lang object. So as long as we want to handle all the situations, we need to actually check what is the superclass of the class we are processing right now, and handle cases where the superclass is not a real class, when it's something different. So now let me do a coding example of how we can use the ASTs. And for that, we will use another annotation, which, when it will be placed on a variable, or it will mean that the variable should only contain valid regular expressions. And we will check whether, if the variable is initialized, whether it is or it is not a valid regular expression. So for example, here we have a variable called pattern. We claim that it should contain only valid regular expressions, but we are initializing it to something that is surely not a valid regular expression. So now we will write a checker that will test and produce warning for this situation. And I will need to cheat a little bit more to see what should be the name. And now, to avoid some complexities with trying to get trees from annotation processors and so on, we will use a framework that is created in this project on the side, and that defines an interface called rule, which basically will give us some context and a compilation unity which represents the root of the AST for one file. And the analysis context is somewhat similar to what is the processing environment inside annotation processors. So now we have, I will close this one. Now we are called, we have an AST root that corresponds to the file we are processing right now, and we need to go through it and find out whether there are variables that have regexp annotation that are initialized to something that is not regexp. So let us start with something simple, and we will need to go through the whole file. So let us do it like this. In this example, we will modify this code later, and now this TreePathScanner will go through the whole AST, and there are methods for each kind that the AST, for each kind of AST nodes, and we can override these methods, and they will be called for each AST node of that specific kind. So for variables, we will override visit variable method, which will be called on all places or on all declarations of a variable. And now we need to check whether the variable has the regex annotation and whether it has initializer, and the initializer is a constant string of and whether the constant string is a valid regular expression or not. So first, let us check whether there is the regex annotation, and for that we will get the element that models this variable in the element world. And for that we will use the trees that we will, in this case, get from the analysis context, which shields us from some complexities with getting the ASTs and so on. And we will use the getElement method, which gets us the element that is attached to this AST node, and we will pass the current TreePath to it. And it's not final. Okay. Now we will use the find annotation utility we've seen before to check whether there is the regex annotation, and if there is, this will return something different than null, so we will continue with our checking here. Now we need to see if this variable has an initializer. That is like one simple case that we can use. And let me do that on tree level in this particular case. If it would be a compile time constant, we could get it also from the element hierarchy, the value, but we won't depend on whether the variable is or is not a compile time constant, and we will actually pull the constant value from the AST. So if the variable tree has some initializer, then we are going to do something, and for now we will simply ask not whether it has an initializer, but also whether it is of kind that is string literal. What I should point out here is that each of the AST nodes or the AST nodes have a method called getKind, which returns us which exact kind of the AST node we are holding right now. And string literals are of kind string literal. That is probably understandable. And so from here we can simply pull out the value of the constant. So I can do that like this. I don't know what's happening. It should show me that it can be casted or should be casted. Oh no. Ah, sorry. Wrong string literal. Yeah, string literal 3. Sorry, I am tired. Okay, I apologize. I am really tired. It's a literal 3 that models any literals, including string literals and integer literals and so on. So we have this literal tree, we get the value of the literal, which is string in this case, and now we will abuse the regex pattern in Java to validate if it's a valid regular expression, and if it's not, we will produce some warning. And for this I won't use exactly the messenger that is used by annotation processors, because it only allows us to add warning on elements or annotations that are annotating an element. I will use a different method inside the trees utility class that allows us to attach an error to any AST node we need. So in this case, we'll produce a warning. I will cheat a little bit more and okay. In this case, I don't need to really cheat that much. We can simply use the description of the pattern syntax expression. We will add the warning to the variable initializer, and yeah, in this case we also need to say from which file the tree that we want to annotate with the warning comes from. That is the root of the AST, and I will format this differently so that it can be seen. So here we are checking whether the constant is a valid regular expression or not, and here we will print some warning. And I have some tests for that. So let me check if at least some of them are passing. So some of them are passing, some of them are not, which is fine. Because these tests test much more than just this simple case that we implemented so far. So let me run just this method, just this one test method that basically corresponds to this example test class, and the test passes. So our checker actually produced the correct warning at the correct place. And now we can play some more with this, fix some more of these tests to see how to use the AST some more. So in this case, we don't have exactly the literal in the variable initializer. We are referring some compile time constant. So at this point, what we need is to look up the meaning of this def mask variable, get its value, and check whether it's regular expression or not. And to do this, I will actually create a method from this for getting the constant. Yeah. So I'm afraid I will need to modify it a little bit because we will need the context in the future. We don't need it right now to get the value of the literal, but we will need it in the future. And now basically what we need to do is to go through various kinds that the initializer can have and resolve them. And I will do one more change here, and that is I will use just a tree and will pass the initializer to this method from here, which will allow us to go recursively in this method. And we will go by kinds, doing whatever is necessary. I will rename this to expression. So if in case we see a string literal, we already know what we should do. We should just pull out the value out of the string literal. If you are seeing an identifier or a member select, which basically means something dot something, and we can handle this together without any real difference. We will need to go from the current place to an element, and for that we basically need to call get trees on trees get element, and for that we need a path, so we need to change the expression to path anyway. And the path class has method called getLeaf, which will return us the last element in the tree path. And we will need to pass the correct tree path to our getConstant method, like this. So now we can look up the element that is being referred at the current place in the AST, whatever that is. And if that element is non-null, this is the defensive coding, and if it happens to be a field, because compile time constants must be fields, then we will pull out the constant value from it. So compile time constant, and the element kind for fields is variable element, so we will use this variable element stuff, and it has this constant value method which returns the compile time constant value for that given field, if there is any. And now if the compile time constant is string, then we can simply return it, and we are done. If the element referred here is not a field for whatever reason, if it's null, if the compile time constant is not, if there is no compile time constant value in the field, if it's not a string, for example, it can be a field of type int, we will simply say, hey, we found nothing. And if the kind of the expression we are looking at is not recognized by this method, we will again say that we found nothing. And we need this check method to validate that that the constant is not null. So I will just add the guard null check here, and we no longer need this test whether the initializer is a string literal, so we will delete that. And now, and now we will run this test to see if we wrote it well. Yeah, we are actually going from we are actually getting the value of this def mask constant. Now we can go on with this example and check, hey, if we have basically a static compile time constant string and adding it to another static compile time constant string, the result is again compile time constant. So we probably should handle also cases like this one, and we can enhance this getConstant method relatively easily. The kind for the plus operator is plus, and we basically get the value for the left part of the and the type of the AST that models plus is binary tree. So we will take a binary tree from the expression, and we will take the value of the left part of the operator of the expression and the right part, see if they are both non-null, and combine them as needed. So we will call this getConstant again. We need to provide this TreePath to get the element, obviously. I see a mistake here. We need to cast the leaf of the TreePath. And we will put the left operand there. We will do that the same for the right operand. And if both of the right and left, let's say, constants are non-null, we will combine them like this. And this should fix this test for us. Okay, it did not. Which is a bit surprising to me. So at least we can test debugging to see what's wrong. Okay, so we are getting the correct binary tree. We are getting the correct left part. And we didn't get the correct right part because we got an exception. That is cool. So let me try to debug one more, and after that if we don't find the problem, we will probably need to move to some other part. I am sorry for this. I made a mistake here. I have a tree path and I am trying to cast it directly to a tree instead of getting the leaf node of the tree. It's a pretty common mistake. I guess we should create a special warning for this one because it happens maybe way too often. Yeah, and now we see this works at least as intended. And now we could go with more of these examples, checking in the case of this test, we are basically calling a method with a constant string, and we would like to check whether parameter marked with the regex annotation is a valid regex when the method is called. But let me skip this example. You could spend maybe 10 minutes on it. So let me show you a different example, which is I think more cool, but it's still manipulation of the AST, manipulation of the source code, or checking the source code. It's still no graphics. Let us consider this variable list of strings, and here we are removing a string from it, which is fine. List of strings typically contains strings, so it's fine to remove a string from it. But on this place, we are actually trying to remove a long from the list of strings, and there shouldn't be any longs in such lists. But this is not really compile time error, because you can pass, if we look up the declaration of the remove method inside list, we will find out that we can pass any object into it. So from the compiler perspective, this is absolutely fine, but from the developer perspective, it's something at least strange. And so NetBeans produces this warning, and we can try to write this warning, like go through the AST and write the same warning. But like one more thing before really going into that. In this regex rule inside the analyze file method, we are creating an anonymous inner class and doing a lot of stuff inside the method, which not only doesn't look really nice on the projector, but it's also not nice when one is reading the code. So maybe we could make it simpler to write the rule by creating maybe abstract rule that will extend the TreePathScanner for us and implement the rule for us, and it will basically say, hey, go through the whole AST on myself, and sorry, I need to do it in the opposite way, and we will be passing the context as the parameter to the scanner, and using this, let me say, infrastructure like abstract rule, we can make this collection this checker for the not very nice collection remove thing easier, at least a bit. So now we want to be called on this piece of code, which is a method invocation. So we will override the visit method invocation method. And first of all, this method will be called on every method invocation in the whole source. And we need to find only those method invocations that are actually mapping to collection remove. And to make that simpler, I have another utility method that allows us to describe the method signature. Like in this case, we are looking for method remove in Java collection that takes one parameter of type object, and I would like to rename this, and it will return us the element for this method, which is executable element. And now we will see if the method invocation we are looking at right now is really method that corresponds to this collection remove. So I will use this the trees mapping again without too much talking, and I will check whether the element is not null and whether the element is a method. The elements also have kinds, so we can check what kind of element we are seeing, and in this case we are checking for method element, and the L element right now represents the model or the element for the method that is being called in the actual source code. And we need to check whether the method that is being called overrides the Java collection remove method. And the overrides relation should also ensure that it's the same method if needed. And for that, there is a utility method inside the Javac APIs on the elements utility class that checks whether one method overrides another. So we would like to see if L overrides the remove method from Java collection, and we need to say also compare to which type, and I will do something relatively simple here, which is this. There are some little twists in why one method can override another method in some contexts and not in other, but we won't go into this much deeper because it's a bit esoteric problem. So now this is a reasonably valid check for if the L method that we are currently calling overrides the Java collection remove method. And if it does, then we need to do some more checking. And this is the point where it gets a bit more difficult. Let me switch back to this example. How do we find out what is the correct types that can appear in the list of strings? We could, in a very complex way, traverse the type hierarchy and map the real type arguments to the formal type arguments and so on. But there is much simpler way to do that. We can basically look at the add method and look at the parameter that takes the add method in this particular case and check whether whatever we pass into the remove method matches the type that can be passed into the add method, and that's it. It can be done in this relatively simple way. And to that, we will use this resolve method utility again that is created for this talk. We will just change it to look for the add method. And now we will use a really cool, let me do it this way. And now we will use a really cool thing in the Javac model. And that is this sMemberOf method. And it basically allows us to say, hey, this add method is declared somewhere in an interface Java collection, and we are holding and we are calling it on an expression that is of type, in our case, a list of strings. Give me the correct type of the method, give me the correct parameters for the method and return type, where all the real type, the formal type arguments are substituted with the correct values. But for that we need to look up on what variable we are calling the remove method. So let me do it here. The method invocation tree has this method select, which basically represents this part of the AST. It's everything before the opening bracket. And if that, and I will do something simpler here, because we don't need the type of this. We actually need the type of this part of the tree. So if the method we are calling is represented by something dot remove, we will take the type of something from the tree, and I will do it like this. It's and now we will just ask the Javac to give us the type, which is traditionally the type on which a method is called site. It's used everywhere in Javac. So basically, what we need to get here is to get a TypeMirror for this part of the source, basically. So yeah, I'm missing a semicolon here. I guess I will need to do it like this. So basically, we are looking up the type of the expression here. As part of this if statement, I will check if it's non-null, if there is something in there, and if it represents a type that corresponds to a class or to an interface, which means if it's a declared type. Declared type is, for example, list of strings or list of numbers. Other types may be, for example, primitive kinds, which is integer or so, and so on. Now we will use this site.
So how does it deal with the wrappers for the primitive types?
Sorry,
How does it deal, like you have a line, a primitive line being used in your add method. Suppose that the add method really took a primitive line. Would it distinguish between a primitive line and the object line?
well, actually, do you mean in the parameter here?
Is it going to look for a primitive line or an object line?
Okay, let me show you a debugging stuff in NetBeans where we can inspect the trees, so we can actually look this up exactly. So this method invocation here has one parameter which is of type long literal, and it's typed to primitive type long. But when the Javac is resolving which method is being called here at this point, it does the boxing unboxing, so it knows that this particular method that we are invoking at this place is removed that takes object. I'm not sure if that is.
It seems like it's ambiguous because of the wrapper classes. Is all I'm trying to do.
Like,
How can you check a type if you don't know what type it is to check?
sorry, I don't really get it. Like, can you give me an example?
Yes, if your function were, instead of being defined with a string, suppose it was a list of object logs. And you're going to then go try to verify that the type of things which have been added to that list really are all object logs, except would it accept the primitive log because of the wrapper classes?
Okay, if for checking whether to check whether the type that we are removing matches the type that can be inside the collection, we will use a method or a utility method that is called is assignable, and it actually checks whether the value can be assigned into a variable of the type. So what that utility method does is it checks whether we can assign this value into this variable or into like the type of the variable L, and it also does the correct boxing unboxing for us. It will be next step, like in a minute or so. So the Java C will do this conversion for us even in this case, I believe. Of course, it will check the source level, and in 1.4 you couldn't do that, so it wouldn't allow the conversion, and we would know that the types are not convertible in this sense for source level 1.4. Okay, so now we have something that models basically that is able to tell us what is this, what's the type of this parameter to the add method. So there is a TypeMirror that models types of methods, and that is called the executable type. And so that is what we will get in this case from this as member of method. It will let me show it. The as member of method will take the element for this add method and replace this type parameter e with the real type for this list of strings. So now we can look up the type of the first parameter from the executable type like this, and its first parameter or add parameter. And now we need to look at the actual type that we are passing to the remove method. So it's what we have, very similar to what we have seen a few times already. And we basically need to take the type of the first parameter. I will format it so that it's more visible. So we are preparing to get the elements and type mirrors from the AST. We need to know the whole path from the root to the actual AST node. So we need to create this tree path every time, and then we simply pull out the type for the given AST node. And now the utility method I talked about, we can simply check whether we can assign an expression of a type into a variable of another type, and is this assignable method. And in this case, we are asking whether the actual type can be assigned to the first, to the add method parameter, and if it can't be, then we are probably doing something strange. So if it seems that we may be doing something strange, we will report a warning, and I guess I will need to okay. I named the class with the wrong name. I will need to rename it so that I can run tests on it. But now I need to take the correct warning that we should produce, and it basically says that the actual parameter type is somehow strange, and that it should be assignable to the add method parameter. Like this, and I will need to look up the root of the AST here as well. So let me make this smaller. So this should probably work, and I will need to rename the rule because the test name doesn't match the name of this class, and so it would be difficult to run the test. Now the test should match the class, and let me uncomment the tests, and let us run some simple one like this one, and it didn't pass. That's great. And yeah, okay, sorry, I always forget about that. The test expects that we will actually pass just the parameter, not the whole invocation of the method, but just the violating parameter. That the warning will be on the violating parameter. I'm sorry for this. So now it should be better. Yeah, so this way we actually checked whether in this case, when we are removing a plain object from a list of strings, that we produce warning for this. And yeah, we can test, for example, by this test that we are not warning about the correct invocations. So the test is passing, and there are quite some. Okay, there are some other tests, but I will probably skip refining the rule to work with them, to give us time for other stuff. But first, let me ask: is that part with the is assignable clear, or? Yeah. Okay. Now, I won't write this now, but there are two things to note for this approach we are taking in analyzing the source code, and for this particular collection remove rule. The first is that in the current concept, each rule we run goes through the whole AST, and if you will have like 200 of them, each of them will go through the whole AST again and again. And this is probably not going to perform very well. So for more production-like environment, we would probably want to say that this rule is interested only in these kinds of AST, so that it would be called only on these kinds of AST, and there would be just one class that would go through the AST and call the rules at the correct places. And for this particular case, what's important to note is that this method invocation method is called for absolutely every method invocation in the source file. So if we do something inefficient in this method, which frankly we do, because we are resolving this method for each method invocation and so on, we are going to slow down the processing a lot. So for real world, we would need to take some care, reorder the checks to make it faster, or what we are doing in NetBeans we can specify some patterns, and the like processing of the rule would be called only on AST nodes that fit that pattern, which makes it much faster and much harder for the rules to slow down other parts of the system. And I hope we will get to this later, but we don't have that much time for later right now. So now so far we have seen how to work with the ASTs on a few simple examples, and now let me talk about how to actually get this AST attributed and so on, and also how the javac itself processes the source file. So basically, as every compiler that produces some executable code, javac has two parts. It has some front end that analyzes the Java source code, if you will, and a backend that actually produces the class files. And for us, most important is the front end, because it produces the attributed AST, and the front end part consists of several phases that run one after another, and basically there are two big front end phases. One is parse, which takes the source code as, let me say, characters, and creates the AST for them. It does the lexical analysis and then parses the source code and creates an AST for that. And then there is an analyze phase that goes through the AST and attaches all of these elements and types to the AST. And this analyze phase has some smaller subphases inside it. The first is enter. It basically finds out what classes are in the source code, what methods are in the source code, and so on, and creates the element models for these. Then there is attribute subphase, which goes through the whole AST and attaches the elements and types on all places, resolves which methods are called at specific places, and so on. And then there is flow, which doesn't really change the AST, but produces compile time errors for definite assignment. If you are, for example, assigning to a final variable, or if a final variable is not initialized, it detects unreachable code. So if you write something after return, it will tell us that you can't do that, and so on. And not completely all, but most of the errors that compile time errors that are reported by Javac are reported when the flow phase ends. The reason why I organize the phases in this way is that using the ComSans source APIs, we can call parse and analyze independently, but we can't really run just the enter and not the attribute and get the results. We may call parse and analyze and get the attributed AST. And just quickly through the backend phases of the compiler that actually produce the class files, the bytecode, there is transtypes phase that strips type information from the AST. So after the transtypes phase, there are no list of strings, there are just lists. There are no classes that take a type parameter, there are just classes. Then there is slower, which basically converts the current 1.6 source code into, I think, 1.1 source code, stripping for each loops. Since 1.5, you can do post and pre-increment on Java.lang integers, so it's also removed by the slower phase. And basically, the lower phase prepares the AST to be simply printed into a bytecode. And then there is a phase that actually takes the simplified AST and dumps the bytecode into a class file. Now, let us see how we can invoke Javac, how we can invoke the compiler. So one option is to use JSR 199, which allows us to construct a compiler tool with some parameters, let it analyze some files, let it create ASTs, attribute them, and even compile the code, I mean produce actual class files. But it only allows us to create a new tool to analyze source code, or if we need that, produce the class files. It doesn't allow us to actually plug ourselves into an existing call of a Javac. On the other hand, we can use annotation processors to actually plug into a running Javac that someone else started. We didn't, we just plug into it. It's good, for example, if you need to auto-generate code, the generator for the meta-inf services registrations that I was using is also written as an annotation processor that generates the entry. It allows us to check some constraints and actually stop the compilation. If an annotation processor reports an error, the compilation will stop. So it allows us to stop the compilation and not allow some code to compile. But there are some problems with getting, let me say, these annotation processors run, when we have seen the phases, the Javac phases, the annotation processors in Javac are run after the enter phase, which is a subphase of analyze. And at that point, the ASTs are not fully filled with all these attributes. And to actually get the attributed AST from an annotation processor, one needs, it currently can be done only in very recent JDK 8, and by very recent, I mean something that is in the JDK 8 TL repository since about last week. So it hopefully will be possible to get the attributed AST trees in JDK 8. This is not possible in JDK 7. So now let me just quickly show you how to invoke the Java C using JSR 199. It's not really difficult. Basically, you can close. Wow, I closed too much. You can close this. Basically, we use a tool provider factory and we ask it to give us a Java compiler tool. And once we have it, we create a task that actually does some compilation or some parsing, and we can pass some parameters to this when creating this task, which, okay, and at least these options here that I am passing to it while constructing it, basically match parameters that we can pass to Java C. So if there is something that you can pass to Java C, you can simply pass it as an option to this getTask method. Let me note, or let me point out this parameter, which is non-standard, but keeps the end positions for trees, because normally Java C doesn't keep the end positions of trees, it just keeps the start position of a tree. So with this parameter, it keeps also the end positions. And while creating the task from the compiler tool, we pass files that should be analyzed, parsed, or compiled to it. And then we can simply call a parse method, which will do the parse phase, the analyze method, which will fill the ASTs with all the attributes. And then in this case, we are analyzing the ASTs, running our rules on them. And okay, I need to peek what exactly test I have prepared here. Okay. I forgot one more thing, and that is register this regex rule using the service provider, so that the infrastructure can look it up. It's fine for the tests, because the tests just call this rule regardless if it's registered somewhere. But the infrastructure that really will run, like from the command line, the rules, it needs the rules to be registered. And now I will run this project, which will run this main method, basically invoke the Java C through the 199 APIs, parse and analyze the test source code for the regex, and report any warnings that the rule reports at least that it should do that. Yeah, and as you can see, this is the warning that reports the rule we created some time ago. So it can be really run through this. The rule is run by this tool that is based on JSR 199 APIs. I will just show you how this can be done in the very recent JDK 8 and what I hope will be possible with release JDK 8. That is, I have an annotation processor, and inside its process method, I register something that is called task listener, and this task listener is then called after each of these compile phases and before each of these compiler phases. And so when the finished method is called, meaning after the analyze phase, we have the attributed ASTs and we can run the rules. And I will use. Okay, I won't actually write this. I will just show you in like 5 minutes at most how the collection remove stuff can be done in NetBeans. It's basically very, very similar to what we have seen already, and we have an infrastructure that is like enhancement of the simple one that we used in this talk. It uses pattern matching, or it allows us to use pattern matching. So this compute warning method will only be called on invocations of remove method of java.util collection. It won't be. This method won't be invoked on any other method invocation, which basically means that if this method is slow, it won't slow down the whole process of analyzing the file, unless there are a lot of calls to collection remove in the source code. And inside this method, it's basically very, very similar to what we have done with the plain Java-C. It checks whether the actual and expected type are assignable or not. It's not really different. And yeah, and this at the top, there's registration into the NetBeans system that defines this collection remove as a warning inside NetBeans. And the real world warning or warning provider that provides the warning that we have seen in the editor is a bit more complex, but not that much. It's very, very similar to the one we have here. So this is pretty close to some possibly code from the real world. I will just before ending. I will shortly say what we have, like explain what we have seen on the example. Inside NetBeans, we use the Java-C to provide warnings and code completion and everything. We have two ways to get the two types of tasks that access the data from Java-C. We have foreground tasks, which like get the data as soon as possible synchronously, and we have background tasks which produce the warnings, for example, and these are run after, for example, change in the editor on the background when there is, let me say, time to run these. Inside NetBeans, we have also some additional features in the model, for example, Javadoc at this time, and we provide AST-based model for writing. And basically, NetBeans hints are warning providers, and it's more or less what you have seen in the example for the NetBeans collection remove. And I think important part is that it can use pattern matching to improve performance and to simplify writing of these warnings. And now, let me conclude the tutorial. Javac is not only a compiler, we can use it as a library to model Java source code. It's used by NetBeans and others as well. It allows us to verify that some constraints that we add to, that are not defined by the language, but that we add are fulfilled. In some cases, we can even stop the compilation if the constraint is not fulfilled. And just to drag you to the following tutorial, in like 40 minutes, we will have tutorial here about declarative way to write the checkers in NetBeans, which is good for some simpler stuff, but for more complex stuff, which includes the collection remove, one still needs to use the Javac APIs, because the declarative way in NetBeans cannot express such constraint. So now, if you have any questions, I will try to answer them. Yeah, please.
Your example with the TreeScanner and the TreePathScanner, you invoke that by explicitly running a program that called Javac from within Java. Is that the only way to start your TreePathScanner to generate the warnings?
Do you mean the main class?
You have some class that's searching through to look for the collection.remove. And it's
Yeah.
based on a TreePathScanner, right?
Yes.
Okay. You called that TreePathScanner by using JSR 199 call Javac from within Java. Is that the only way to call it?
No. Like in 7, I don't know about a really better way, but in 8, it hopefully will be possible to get the attributed AST from the annotation processor, so that you could plug into the Javac using the annotation processor. Which would mean that all this stuff with JSR 99 wouldn't be necessary at all. Okay, thank you. Please.
That processor works in the class file, not the Java. So you can go, so it starts from the class file, even if it's called Javac. It's parsing the .class file.
Inside annotation processors, what's in the root environment, root elements, it can be either from source or from class file, depending on how the Javac was invoked. But it's more typical, I think, that these originate in the source files. Like I think that the most typical usage of Javac is that it processes the source file. One can really specify classes on the command line of Javac, and it will run the annotation processors and give them the elements for these classes. But I don't think this is very typical. And with that task listener stuff, this really gets called only for ASTs that must originate in a source file. Okay. Thank you. Thank you for your question. Please. Yeah, there in the presentation, sorry, I'm confused about what's up and what. Yeah, there is a project on Bitbucket, and in the download section there is a zip file that basically corresponds to what I was using here, and there is a repository, and in the trunk of this repository there are also the rules implemented, so that one can really see how the implementation can look like to fulfill for the test to pass, basically. Okay, so any other question? Well, thank you to attend to this talk.